Hello everyone, this is Cameron Snow with Danomics.com. In this video we're going to be talking about how to get your data ready to be interpreted. So when we think about starting a new project, one of the things that we need to do is get our data in the correct shape to be interpreted. So in terms of what this means, it needs to be clear what our data is. It needs to be consistent. So we need to make sure everything's in the same units, same lithological reference. It needs to be complete. By this I mean, if we have multiple logging runs, for example, we need to make sure we have all of those available to us to interpret, so that we're not missing any data, and it needs to be clean. So we need to have identified outliers, we need to have repaired bad data, etc. So for those of you that have worked with log data before, you know that it suffers from just several problems inherently. Probably the biggest challenge when a lot of people are starting is curve mnemonics. You know, but the problems go beyond that. First of all, like we have multiple logging runs, so you can have data spanning across different files. There can be unit differences. You can have, for example, things reported in either like a density porosity or as a bulk density. You can have things reported in decimal, you can have it reported in percent, and so on and so on. So there's a lot of different potential units. And then also there's lithological references, which can be a bit more challenging to deal with. So this is, for example, when the vendor logs something, for example, in sandstone units, because that's the target of interest for one well, but then the next well it's logged in limestone units because that's more of a global reference. So there are things along that we need to pay attention to, because especially when we're looking around the margins, that can be quite important. But then the other problem is, data can be misrepresentative of the subsurface. So, we can have washouts that lead to bad hole. A lot of the data you get is digitized, and sometimes not enough care has been put into that. So there's things that we need to do to correct that. And then there's also just the underlying variation in tool response from different generations, different vendors, etc. So, at Danomics, we view this as kind of a two-part solution. The first part is dealing with data attributes, and that's things like mnemonics, units, lithological references, and curve compositing for multiple runs and files. And then the second part of that is data quality, which is dealing with handling washouts and inconsistencies in the scale. So those are the two tracks that we're going to talk about, and we're going to start with this data attributes first. So when we think about curve mnemonics, there's about 20 to 30,000 different curve mnemonics in use. These vary by vendor, tool type, tool generation, etc. The importance of these mnemonics and the scope varies a lot by curve family. So for something like a gamma ray or a neutron, this can be very, very important to get nailed down. For something like a D-row or a PE, there's only a handful of mnemonics that are out there for them. So maybe a little bit less important, but you still want to get that taken care of. In terms of the number of mnemonics that you need to worry about, with about 100 curve mnemonics, you can capture about 50% of the data that's out there from my research. If you get up to about 500 curve mnemonics, you'll get about 75% of the relevant data. And it's not until you get to somewhere around 5,000 curve mnemonics that you have 95% of your data captured. And when I say 95% of the data, I mean out of the significant curve names. So things like your standard triple combo, so gamma ray, medium, shallow, deep resistivity, a micro resistivity, neutron density, PE, plus a sonic curve, plus caliper, etc. So it starts to take a significant effort to capture upwards of 95% of your data. And one problem with this is it's not just what comes from the vendors, but it's also what comes internally. So a lot of times users often inadvertently create new mnemonics by appending an _1 or an _2 onto the back of a curve name, which means that we need to then add that to the aliases. So when we talk about curve aliases, essentially this is just a dictionary that helps you, you know, work with just one curve name. So instead of looking at, for example, a deep resistivity where it maybe is DRes or ResD or AF90, etc., we're just going to be looking at one curve name, and we'll need to, you know, take some care when setting this up. So, you know, how much granularity do we want? Do we, for example, want to just look at all resistivity curves, or do we want to look at it by depth of investigation? You know, I would say it's better to be a bit more granular because we can always combine things later, but then it takes a lot of effort to split things out additionally. You know, for a lot of softwares, Danomics included, the order of precedence is important. So what I mean by that is within the alias table, you know, what are the curve names that you're looking for first? So unfortunately, building this out, it's a very manual process. It often requires a lot of expertise because you know you need someone that can understand you know what mnemonics are part of each curve family. And it's also something that as you go through and you acquire more data, you're going to have to keep revisiting this and analyzing your files to make sure that you've captured a significant portion of the data. One thing I will say is in Danomics, we have an alias table of somewhere between 7,500 and 10,000 curves already built in there for you. So you should be capturing somewhere in that 95 to 99% data range using our software. With curve units, LAS files should have curve units in most cases. However, the LAS is still valid without curve units. A lot of curve units have their own mnemonics associated with them. Curve units can be wrong, and depending on where you're working, sometimes it can be metric, sometimes it can be imperial, sometimes it can be mixed. So just real quickly on units, what do I mean that they also have their own mnemonics? So for example, you know, if we look at, let's say, the sonic curve here, we see that here it's called microseconds per foot, or US per F, and that is the standard imperial unit for that. But you might also see that abbreviated differently. So it might be written out microseconds per foot, or US per FT, or US per FOOT. So there can be different mnemonics there. Same for density, for example. It could, you know, here it's grams per centimeter cubed, but it could also be G per cc or G per cm3. So there can be a lot of different indicators of the unit there. So you need to make sure to pay attention to that as well. With respect to curve units and families, what I mean by this is there are the same tools, it's the same measurement, but they're just reported differently. So for example, there's a difference between the density, porosity, and the bulk density. You know, it's obviously the same tool. However, you know, these are different. One is in, you know, decimal or percent, and the other is in grams per centimeter cubed or kilograms per meter cubed. And often there can be multiple choices here. You could have a DFE for sandstone, a DFE for limestone, a DFE for dolomite. In theory, it's a simple operation to convert this back, but there are some potential unknowns. You know, what was that matrix reference? What's the fluid density that they used when they calculated this? So, you know, there are some subtle issues there that can affect your outcome. So when we look at curve units and how we want to handle these to get our data interpretation ready, there are a few different ways you can go about this, but I will give you an example of kind of how we do it in Danomics. So first of all, we read the curve name. So for example, We see that it's a D-Fee sandstone in this case. Then we check to see if there are units. Is this decimal or percent? If the units are known, then we can go through and we can convert that back to grams per cc. If if the units aren't reported, we'll go through. Is the average here less than 1? No. Is the average here greater than 1? If the average is greater than 1, then we know that's in decimal, so we'll convert that to decimal. Or we know it's in percent, we'll convert that to decimal, and then we'll convert that to grams per cc. So there are some techniques here you can use to infer what the units are without actually having those reported. And even if the units are reported, this provides a good second check to allow you to get to the correct end point. So finally, we have lithological references. These references are how the data is recorded. So as we mentioned on the density porosity, for example, there's a calculation reference. Did we use a limestone, a sandstone, or a dolomite reference? For the neutron, there's also a reference. Is it a limestone, a sandstone, or dolomite? Again, there are vendor-specific conversions that need to be done on something like the neutron. So it's important that we take that into account, because it will create a shift in your data of a couple of porosity units. So when you're working with something that's already low porosity, that can be a pretty significant shift. And the best way for us to know how this was measured is really by trying to understand the curve mnemonics and making sure that we had those looped in. So this all starts to tie in together. Not only is it just a neutron curve, but also is it a neutron that was logged in sandstone units, a neutron that was logged in dolomite units, etc. So we need to make sure that we understand that, and then we've built the right level of granularity into our data table. And then finally, once your data is aliased and you have the units consistent, you've got the lithological reference correct, then it's time to put together multiple runs. And so, a lot of times this also ties in together with the aliasing. So we can go through at this point and and stitch our logs together, but we need to make sure that we aren't compositing things that have mixed units or mixed lithological references, because once you do that, you really can't make changes without creating some errors. So if you stitch together a density porosity sandstone and limestone together, then if you convert one or the other over, it's not going to be correct for the whole. So we need to keep those separate. So once we have gone through those steps, our data has been preconditioned to have clear and consistent names via the curve aliases, consistent units as we have gone through and done the conversions there, consistent lithological references as we have analyzed for the reference that it was logged in, and then finally we've made sure that it's a complete data set. So we've got 3 of the 4 C's. It's clear, it's consistent, and it's complete. Next thing we need to do is make sure that the data is clean. And this is where we really start to move from data conditioning into data interpretation. So start off, curve normalization is one of the options that can be done to help clean your data. There are a few different ways you can do this. You can do shift operations, which essentially you take a curve and you add or subtract an amount to it. So I'm showing in this that we are shifting the data over, and this can be shifting so that your minimum value is a certain value, can be shifting such that your mean is a certain value, and this can be, you know, either relative to an absolute relative to another well, or it can be an absolute value that you're shifting to. There's stretch and squeeze operations. So you can do min-max scaling, you can do relative scaling, you can scale based on percentiles. So that's my personal favorite. I like to you know, scale wells so that their P10 or their P90 distributions roughly line up if I'm going to use normalization. You can also do some things like a shift plus a stretch and squeeze, or an asymmetrical stretch and squeeze. Um, the only caution here is that the more sophisticated you try to be with your normalization, the more care that you need to put into it, because you can really start distorting trends in the data if you're not careful. Um, so with these kind of standards in place for either a shift or a stretch and squeeze or some type of three-point operation, when should we apply these? Okay, so with respect to when to normalize, you know, when you have sufficiently large data sets where you can't set parameters on a zone by zone and well by well date basis, normalization can really help you make better interpretations quicker. Um, when your overall data ranges are relatively similar, and from an academic perspective you expect them to be very similar, you know, it's a good time to normalize. When you have multiple vendors and, you know, multiple generations of tools, you can also normalize then. And then one other consideration is if normalization helps you with your ability to correlate, that's also a good use of normalization, because you can normalize, use that to help you establish a correlation across the field. You know, so when you're picking your tops, and then you can turn off that normalization and use the raw curves again. Um, there are certainly times when you shouldn't normalize your data. You don't want to do this if you have geological changes that are driving those, because then you're starting to erase out the geology. So, for example, if you were going across the Permian Basin and you went from the Midland Basin up onto the Central Basin platform, you're going to see a big facies change, and you don't want to normalize out that facies change. So, you know, you should avoid that. If you have both compacted and uncompacted sediments, you know, within the same well, remember that if you're doing for example, a min-max scaling there, you want to be careful, because, you know, now it's really a couple of different systems that you're normalizing across. Um, so you have to put some additional care in there. Maybe only normalize using the statistics from a certain range. If you haven't done your unit conversions, don't use normalization to try to fix that. You know, don't use normalization to try to, you know, squeeze a percent down into a decimal range. That's just, there's better ways to do that. And also don't try to fix bad data with normalization. You know, that's a separate process. Um, so any curve can be normalized. However, you know, you most often see this applied to the gamma ray. And if you're normalizing something like resistivity, you know, special care needs to be put into that, because that is a curve that's, you know, on a logarithmic scale. So you should probably use some special normalization techniques to handle that. A couple of things to watch out for when normalizing. You know, if you have you know, bad or errant data points. So, for example, you've got you know, some erroneous values or null values. You know, that can really skew your data. Um, and if you're doing something like min-max scaling, obviously one data point, you know, that either skews your min or your maximum can really affect that normalization and make it, you know, essentially useless. Um, the other thing that I mentioned earlier is if you have compacted and uncompacted sediments, you know, those uncompacted sediments, the density will be significantly lower. Often you're in fresh water, so the resistivity will be significantly higher. So if you're going to be looking at uncompacted sections, maybe you don't want to use the statistics from those when you're evaluating your older, more consolidated sediments. So just something to be aware of there. Okay, the other thing that we need to do as part of cleaning our data is we need to handle washouts and bad holes. So we need to identify where the well bore has washed out, understand what curves have been affected. In most cases, this will be the density curve that's been affected. That's the one, it has a very shallow depth of investigation, so that's why we focus on that quite a bit. It's also one of the most important logs for understanding porosity. We also need to understand what curves are reliable in washout zones. So curves like neutron and resistivity and gamma ray, these are often very robust in washouts. Most modern sonic logs have a relatively deep depth of investigation, so you won't often see bad hole effects in modern sonic logs either. The other thing here is we need to make sure that we aren't that we aren't lumping abnormal lithologies in with bad holes. So if you have coals or salts or other low density materials, these can often be mistaken for a washout, but we need to try and take care to avoid flagging those. Okay, with respect to how we can actually determine what's bad hole and what's not, we can use the caliper log. That's a really good way to determine when the wellbore has been washed out, obviously, but we need to consider bit size with that. We can use the D-row curve. The D-row is the density correction. It's specific to the density tool, obviously, and when we see those D-row values start to kick up, that's often a good indicator of an unreliable density curve. We can look at things like wellbore rugosity, and we can also look at cross plots of different curves to see where data is falling off trend. So let's look at an example of this. So here we have an example log, and in this one we can see that there are some suspicious looking zones here in the log. This up here we see the density dropping down as low as like 1.9, 1.95, which would imply more than 30% porosity. That seems unlikely, so we need to flag this as washout so we can then try to exclude this from our analysis or repair the logs. So first of all, we can flag it essentially by the density value if we want to, but we need to do this on a zone by zone basis, because here we have a chalk, and then above and below it we have shells. So the washout or a bad density value in one is not a bad density value in another. We can do it via the D-row curve. Here we can see that the D-row corresponds quite nicely with where we have these suspect values. But once again, that's something that needs to be done on a zone by zone basis. When we're looking at the caliper log can do a really good job of showing us where we have washouts, of course. The problem is that works great for one well, but when you're scaling up to multiple wells, we need to take care, because different operators are going to drill the wells in different ways. They're going to have different bit sizes, etc. So a 10-inch caliper reading in one well may be perfectly engaged, while in another well it may be severely washed out. So we need to understand the caveat there that we need to either use bit size as part of our analysis, or maybe we need to use other indicators like the D-row or rugosity curve, for example. Also, when you look at the edge of some of these zones, you'll see that we often don't flag all the washout, and so in that case, you need to consider filling in some of the gaps in these washouts, and you can do that, by using a number of different techniques, but trying to use some some edge enhancement here to pad out your Badhole flags. And you can also, instead of doing it in log view, you can also look at it in cross-plot view, where you can try to flag data that is off the trend. Once again, this needs to be done on a zone-by-zone basis. Um, but the caveat here is that uh, you know it's not terribly consistent from well to well, because what may be perfectly valid in one well may be invalid in another, especially if you're looking at something like the density curve that's affected by gas. How can you differentiate at scale a gas effect from washout? So this needs to be done as kind of a one-off process, as opposed to looking at some of the other logs like the D-row or the rugosity. Okay, so once you flag the washout, what do you need to do with it? A couple of different thoughts here. You can null out the data. Um, Essentially, that's blanking out your curve so that it's not used in future calculations. The benefit of doing this is that you are certain that you're not using that bad data in any calculations down the road. The downside of this is that you're going to have gaps in your data, and often gaps in zones that may be of interest. So um, if you can live with that, that's certainly one safe method to handle it. The other thing you can do is you can switch to alternative methods when there's washout. So you could say, if it's not washed out, use the density; otherwise, use the sonic porosity, for example. Um, However, this is going to be creating a little bit of extra work for yourself, because you're going to need to calibrate one method against the other. It also means that you need to have a larger data suite available to you, because obviously you can only switch to using a different method like the sonic porosity if the sonic log has been logged. Um, or you can take an approach like we do in Danomics, which is to try and reconstruct the curves. So essentially, you establish some relationship between curves. We do this automatically using automatically generated machine learning models like multiple linear regression and random forest. These can be quite useful for predicting log values and washouts, but you just need to understand the range of uncertainty when you're doing that. Um, so, for example, here's how you could do it using the Gardner method and the sonic curve. So you can see that here we have washouts, and this black curve represents the reconstructed density. And you can see in this case that the sonic, does a really good job of matching the density here. But this is a correlation that is local. You need to calibrate this to the lithology and really, to a number of other factors to make sure that you are getting an accurate reconstruction. And it definitely works better in some zones than in others. So we can see it works quite well up here and quite well in this zone, but it doesn't work very well at all through parts of this interval. When you're looking at machine learning for curve prediction to try and fill in these washouts, there are a few caveats here. First of all, a lot of companies just use this as a buzzword. So you need to understand what's actually going on behind the scenes and what methods are they using. We tend to use MLR, so multiple linear regressions and random forest. Some other softwares, offer things like neural networks, etc. Machine learning models, they require that you do have some good data. Um, and you need to understand, what's your capability of handling disparate data. So in Danomics, we build these models automatically based on the data that's available. However, that's not something that all companies do. So if you're using different software, you need to understand what happens if, for example, you're trying to reconstruct density using a sonic log, and that sonic log isn't present in a well. Can you still do it with just gamma ray resistivity neutron? So, and then, like I said, understanding the not only the accuracy but the repeatability of results from well to well is quite important. Um, with machine learning, of course, there's the question of what curve suite to use. What do you do if that varies well to well? What if it even varies within a well? What if in the top half of the well you have a sonic curve, but deeper in the well you don't? Um, so hopefully your software solution handles that for you. Um, and remember, there are a lot of potential variations that you can use. So if we think about trying to repair a standard density curve with a quad combo, we can use all the available curves. We can only use, one or two of the curves if we want to. There's something like about, for most of these, somewhere between 30 and 40 different combinations that you may want to test. We do that automatically for you in Danomics behind the scenes. But for a lot of you that aren't using our software, you probably have to do this manually. And when we look at how this works in practice, so here we can see the reconstruction shown here in red in this case. So we can see that we're getting a very good fit here in our previously washed out intervals, and we're almost getting an exact match in the intervals that were not flagged as washout. So pretty good results there. Okay, so once we've done those steps, the normalization and the Badhole ID and repair, that is essentially the end of our phase 2 of the getting our data interpretation ready. So now we've made it to have consistent ranges with the normalization, and we've cleaned the data so that we have reconstructed the curves in these washout intervals. So now I want to go into some of the specifics of how we do this in Danomics. So we try to focus on automation for a lot of the data preconditioning. So pre-built alias table with over 5,000 curve mnemonics. The curve units, they're automatically read, statistics are automatically evaluated, and conversion is applied. The mnemonics are used to evaluate the lithological reference. We have built-in correlations, so we can automatically transition those to the correct lithological reference for your calculations. And then we automatically composite these together based on an order of priority in the alias table across all your data loads. So, we have tried to automate the entire first part of the interpretation ready data workflow. So the second part of this, log normalization, we offer both relative and fixed value scaling. The relative scaling, it normalizes everything relative to some key well. So for example, you can align the P50 of the SP for all the wells. You can stretch and squeeze all the logs such as the P10 and the P90 in the key well, and all the target wells align. Fixed value scaling, for example, you can set the P10 to 0 and the P90 to 0.3 for a neutron, or you can do a min-max scale on the DT by choosing a very low percentile and a very high percentile, and setting that to 40 and 100, for example. So we try to offer you a lot of flexibility, but the key is that we try to make this something you can do with a single click, and then it's applied to all the wells essentially instantaneously. And once again, this is just the schematic that shows you how that works with shift, simple scaling, and advanced scaling. One of the key things after you do this normalization, it's important to go through and QC the results of that. And there's a couple of different ways that we do that. My personal workflow for this is I go through and I generate a map that shows me the average values on a zone by zone basis. I'll go through and inspect those, and then I'll look for bullseyes that are consistent across multiple zones. what I'll then do is I'll select my normalization method and I'll apply that, and then I'll generate a map that will handle that looks at how much each curve has been normalized by, and then I'll go through and I'll look at those property average maps again to see if I've been able to eliminate some of the spots where we felt like we had trouble zones. So you can see that as we move through this, we have a way that we can kind of trace what's been done, and then you need to iterate on this on an as required basis. And then finally, for Badhole and ID and repair in Danomics, we have a number of pre-built criteria for you to flag Badhole on. So once you've then flagged that Badhole, we have options to repair it with multilinear regression, to repair it with random forest methods. And what we'll do is we will automatically build and evaluate every combination of model based on your available log data, and then select the best model for that well, and we do that on every well in your data set. We also have options here to pad out the Badhole flags, so you can make sure to capture all of the intervals that need to be flagged as Badhole. We also have some options to kind of blend your repaired curve and your original curve, so when you're on the edge of the washouts here, you can take a bit of a weighted average so that you can have a smoother profile and transition across non-washed out to washed out zones. So that's how we do it. I hope this video was useful to you. This is for us, getting the data interpretation ready is quite important, because if you don't have that part done, you're going to spend a lot of time on the backside doing QC work and troubleshooting problem wells. So we think it's important to get that done up front before you start your analysis, and to make sure that that all of your data, it's clean, it's consistent, it's clear what it is, and that you are working on a complete data set. All right, thank you very much. If you would like to learn more, you can contact me at csnow@danomics.com, and we can try and help you get your data interpretation ready. Thank you.